Hello everyone, my name is Andrew Kim and welcome to my fourth lesson of the AP Physics C review session. Now as you can see, I'm really tired. Because it's 2:40. But don't worry. By the way, this is my last video. Of course, it's not my last video. You have the RLC circuit video and the E&M video, but I am recording this video at the end. So I recorded all the videos before. For some reason, I don't know, my schedule's just messed up. And now I'm recording my last video. So I'm so happy. And my tension's so up right now. So I don't know, whatever. I don't even know what I'm saying by this point. But let's get started. So anyways, yay. Lesson 4, magnetic field. It's all about magnetic field. So I've already talked about electric field and how electrostatics work. Now I'm going to talk about magnetic. However, it doesn't mean that I'm literally going to talk about magnets. I'm not doing that. Holy cow. Instead, what we're doing over here is we're going to talk about the magnetic field caused by the electric or the current. So we're not talking about literal magnets, but what's interesting is that electric current can also induce magnetic field. And how that happens is, first of all, you would have to know something called right-hand rule, and I'm going to explain it right over here. Let's say you have a wire, and you have a current flowing, I, rightward. Then you use your right hand, not your left hand, but your right hand. And basically, place your thumb towards the direction where the current is flowing. So in this case, it will be right. Next, you wrapped your fingers, the other 4 fingers, around your right finger or around your thumb. And the direction that your other 4 fingers wrap around would be the direction where the magnetic field is formed. Now, if you ask me why the magnetic field is formed in this direction and why is it formed in the first place, I do not know. I'm not going to explain about it here. I'm just going to tell you that if you have a current flowing, that around that current circularly, you will have the magnetic field form. And that direction can be either clockwise or counterclockwise. And that direction is decided by the right-hand rule. So if you have a current flowing rightward, then you place your thumb rightward, and the other 4 fingers that wrap around would be the direction of the magnetic field formed, and you have the current flowing the other way, then of course you would have the 4 fingers wrapping around the wire in the opposite direction, and thus have an opposite direction magnetic field. And of course, the notation for the magnetic field is B, capital B, and the unit of it is T. Tesla, let's go, Elon Musk. Anyways, you use T or Tesla. Now, we can induce magnetic field in 3 different types of wire. First is linear, easy, we've just talked about it. Second is a circular wire like this. And fourth is a solenoid. Solenoid is basically a much more complicated version of circular because it's literally just circular circuit, except you have the circular circuits continuously repeating. So that's what it is for solenoid. But anyways, let's start talking about linear. So if you have a linear circuit, then as I mentioned, and if you have a current I flowing on the circuit, then around the circuit, you have the magnetic field formed. But of course, the magnetic field around this, around that, and around this would all be different. Depending on how much far away you're talking about regarding the circuit, of course, you would have different amount of magnetic field formed, right? And of course, we can assume that the farther you go, of course, the magnetic field formed by your circuit would be less because you're simply farther away. So, and in fact, we have an equation for that. Magnetic field B equals to K times I over L. Now, K is a constant. It's 2 times 10 to the power of -7. I is the current flowing on your circuit. I mean, think about it. The current is literally what what it induces the magnetic field. So if you have more current, then you would have more magnetic field induced. If you have less current, if you have zero current, then you won't have any magnetic field induced. So of course, I, or current, is proportional to the B, or the magnetic field that's formed by the current. And as I mentioned, R would go on the denominator, simply because if you have greater R is, by the way, the distance from the point to the circuit. Of course, that distance increases. It means that you're getting farther away from the circuit. Thus, the effect, the influence from the circuit would decrease. So, of course, the magnetic field formed would also decrease, and that's why R and B are inversely proportional, and that's why R goes to the denominator, and you get this formula. Yay! Now, the second thing we have to talk about is the circular circuit. Now, if you have a circular circuit, what's different from the linear circuit is that, I mean, of course, we can use the right-hand rule, but it's kind of hard, right? Because the circuit is this time curved. So to which direction the magnetic field is formed would be different at every single point. Because before, every single point are just lined up. So if you use the right-hand rule, of course, at every point, you would have the magnetic field wrapping around in the same direction. But now if it's curved, like a kielbasa sausage is a sausage that looks like this. I'm pretty sure you've seen it. Anyways, if it's wrapped around like this, then it's harder to use the right-hand rule and actually determine where the magnetic field is formed. However, you just have to do the same thing. Now let's think about this specific point. At this point, where would the magnetic field be formed? Well, use the right-hand rule at this point. Place your right hand on this point and place your thumb to the direction where the circuit is flowing. Now, you might think, Andrew, where is the circuit flowing? I mean, your thumb is straight, whereas this circuit is round. Then how do you place your thumb to the direction where the circuit is flowing? Circuit is flowing in a round direction. Does that mean you have to like curve your thumb or something? No. The direction of the current at a certain point would be the direction of the tangent line at that point, right? I mean, let's think about calculus. What is the slope at a curved line? Well, it's the slope of the tangent line on that point of the curve. We do the same thing. Think about the tangent line at this point. That will be the direction of the current at this specific point. Thus, you just place your thumb on this direction and wrap the other four fingers. Now, the direction where your four fingers wrap around would be the direction where the magnetic field is formed. Ta-da. Now, you do this for other points as well. What you're going to notice is that for magnetic field formed by all these three different points, the magnetic field is going to be formed in a direction that goes in towards the, so it's gonna look like a toilet. So if you have a toilet, and if you if you finish, oh my gosh, it's going weird. Let's say you just flush the toilet. What's gonna happen? You would have water falling in towards the middle of the toilet, right? Same thing's gonna happen. You're gonna have magnetic field falling towards the middle of your circular circuit, because magnetic field at every point, if you wrap around your four fingers, then you'll notice how it always falls towards the middle of the circular circuit. So that's where your magnetic field would be formed. Thus, in the exact middle, where would the magnetic field be formed towards? Well, it will be formed in a direction that goes under into the screen, right? Like a toilet again. So how we express this is, of course, if you have a magnetic field pointing rightward, then you can just express it like this. And if the magnetic field is formed left, then you can just express it like this. But when it's pointing towards the inside of the paper or coming out of the paper, then it's kind of harder to draw, right? Now, what we're going to do is we're still going to use the arrow notation. But now we're looking at the arrow from the top-down view. Now, what's happening is, think about it. If the arrow is pointing towards inside of the paper, it would look like this. Why? Because think about an arrow, like an actual arrow that people a long time ago used. It looks something like this, right? So you have the feathers at the end, and that feathers, if you look from the back like this, the feathers are going to look like this because they're like crossed. I hope you get the point. These are each like feathers. And then this part would, if you're looking from the back, it would look like a cylinder, right? It would look circular. That's why you have this circular part over. So this is why if you have a magnetic field pointing towards inside of the paper, then you use this notation as how it would look like if you look at an arrow from the back. Now, if you have the magnetic field popping out from the screen towards you, then how would it look like? Well, what would an arrow look like if you're looking at the arrow from the front? It would look something like this, because all the back part would be hidden because of this cone part. And how the cone would look like from the front is that it would look circular and you would have this vertex at the end. So this is how you know how you notify that the magnetic field is being formed on a direction where it's popping out from inside of the screen to outside. But in this case, that's not the case. The opposite case would be the case. So you would have the arrow popping towards inside of the inside of the paper. So that's how you do. And if you want to calculate the magnetic field formed in the exact middle of the circuit, then you use this formula, B equals to K times IR. In fact, the formula of this circular circuit and this linear circuit are literally the same. They're both B equals to K times I over R. However, this K, or the constant of the two, are different. The constant for linear was 2 times 10 to the power of -7, but the constant for the circular circuit would be 2 pi times 10 to the power of -7. So you have this additional pi added. Now, it's not going to be painfully hard to memorize this formula because 2 pi, and this pi actually makes sense. Why? Because it's a circular path. In circle, you can correlate circle with a pi, right? You can kind of connect it and memorize it. So it's not going to be too bad. Now, the next thing you have is a solenoid. As I've mentioned in the previous video, if you have a solenoid, if you have a current flowing on the solenoid, basically you would have magnetic field induced. And as mentioned in this video, but earlier, the solenoid is basically a circular circuit, but you just have this repeating circular circuits all continuously, just one after one, right? Because each of them is basically a circular circuit. So if you consider it that way, it's not going to be too bad. Now, again, let's use the right-hand rule to determine where the magnetic field will be forced towards. Now, place your finger on the direction where the current is flowing. Let's think about this position. Current is flowing this way, so you put your thumb this direction, and you have your fingers wrapping, which means the current will be, the magnetic field will be formed in this direction. Let's think about a different point, this point. At this point, you would have current moving. Dun, 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 dun. You have current flowing down. So you have current flowing in this way. So if you place your thumb like this, your right thumb, it's gonna look like this. Thus, you would have current flowing in this direction. Now, from both directions, what you can notice is that the current is, again, if it's a toilet, if the solenoid was a toilet, you can see how it looks like the magnetic field is formed in the direction where the magnetic field actually moves towards, like sinks towards the middle of the solenoid, like how the water sinks towards the middle of the toilet. So meaning that if you add all these points, all the magnetic field induced in each point of the solenoid, you can get the result of something like this. So you have the magnetic field being formed through the middle of the solenoid towards the right direction. So that's what you have for solenoid. And if you want to calculate that magnetic field at the middle of your solenoid, then you can calculate by this formula, K and L. Now, L is the number of times the solenoid is wrapped. Sorry, that's N, and L is the length of the solenoid, and K is a constant, and that would be 4 pi times 10 to the power of -7 for solenoid. Great. So that was all about how magnetic fields are induced. And now I'm going to talk about new things. First is FBI warning. FBI warning! Stop! Freeze! Put down your weapons! FBI warning. Now, basically FBI warning, well, it's a way to memorize things. It's basically that F, force, B, magnetic field, I, current. If you have a current and if you have a magnetic field, then you have a force induced. Now, what this is basically, if you have a magnetic field like this, I'm gonna omit. I'm not gonna draw all the arrows because I'm just gonna draw one arrow to just tell that in this square there's a magnetic field formed towards pointing inside of this paper. Now, if you have such magnetic field, and if you have current, again, what is a current? Current is basically flow, an opposite flow of the direction of movement of an electron. So if you have electron moving right, then the current is basically the flow, the opposite flow, thus left. In other words, if you have an electron moving on a magnetic field, basically, it means you have magnetic field, B, and current, the opposite direction of the movement of your electron. Thus, you would, what FBI warning is telling is that you would have force induced. And how the force applies is it applies in the direction of FBI. This hand sign, look at this. Look at this hand sign, F, B, and I. F, force, B, magnetic field, I, current. It's painfully easy to memorize because you just move from high to low. FBI. Thumb, second finger, third finger. FBI. This is the direction where the force is induced. If you have a magnetic field pointing towards this finger and the current pointing towards this middle finger, now when you say current, it basically means the opposite direction of the electron. So if you have an electron moving, then you would have to take the opposite direction of the movement of the electron. And if you have a proton moving, then you literally just use the direction of the proton moving because proton is the opposite of electron. Thus, the opposite movement of electron would be the normal movement of proton, which would be equal to current. So again, direction of current, direction of magnetic field. If you have these two, then the direction of force applied onto the electron or onto the particle would be this right thumb direction. So again, F, B, and I. Now, this is so easy to memorize because what do FBIs use? They use guns, right? FBI, it's a gun. It's a gun hand sign. And it literally has FBI direction. That's why you use this all the time. One thing to memorize is that when you use this FBI hand sign, you have to use your left hand, not your right hand. So for right hand rule, it's only for this right hand rule. The direction of your current and the direction of your magnetic field like this. And then, because it's right hand, right? So this hand sign makes more sense because it's right hand. You're not going to use your left hand for this hand sign. And then you have left hand side for FBI. So FBI, when you shoot a gun, use right hand. When you do this hand sign, use right. Just understand it in a way you can understand. So FBI, that's how it works. Left hand. And when I teach this using left hand, Dr. Belcher hates it because he thinks it makes things more complicated when I use two different hands, but it's not hard, right? Left hand, when you shoot, just remember this, when you shoot a gun, use left hand, FBI. When you, right hand for this hand sign. So yeah, that is how the force is induced if you have B, the magnetic field, and I, the current, or the particles moving, which can be interpreted as a current. The next thing is Bill Yates, can you sign this bill? Basically, this is the force that, now what's interesting is that not only a particle, but also literally a wire that has current flowing would also be induced force. Because wires are literally a platform for particles to move. So if a particle moves and gets force induced, of course, the numerous particle inside the wire moving would also get force induced. Thus, it's so obvious that if you have a wire on a magnetic field, then of course the wire would also be induced force. And that force induced can be calculated under the formula F equals to Bill Gates, can you sign the bill? Bill Gates, can you please sign the bill? Bill appears twice and you have sign. That's why it's so easy to memorize. Anyways, so you use this formula to calculate the force induced onto your wire. B is the magnetic field. I is the current. L is the length of your circuit or wire, and sine theta. Now, when I say theta, theta is the angle that the magnetic field and your circuit makes. Now, in this case, sine theta would be 1 because theta would be 90 degrees because your magnetic field and your circuit is perpendicular over here, right? So in this situation, you won't have to worry about that. But there are some situations where your circuit would be not placed perpendicularly to your magnetic field. In that case, you would have to calculate the angle between the two and put that inside sine theta to calculate F. So that's how you do. Now, I missed one important thing for FBI. You also have F equals to barbecue or BVQ. This formula is basically the amount of force that a particle feels when it's moving on the magnetic field. So F equals to BVQ and F equals to BIL sine theta are basically like the same formula, except F equals to BVQ is the force that a particle feels, whereas F equals to BIL sine theta is the force that a circuit or a wire feels. So that's the difference. But anyways, that's how you do. Now, if you want to figure out which direction force applies onto a wire, same, use FBI. Now, F would be the direction of the force that's applied, so that's what you want to find. And B would be the direction of magnetic field, which will be given from your problem. And I, the current, the direction of the current is literally the direction of the current flowing on your wire. So you can use FBI to figure out to which direction the force is being applied onto this wire. Easy. Now, the last thing I want to talk about is how you connect these things to mechanics. As you can see, F equals to BVQ. You have F formed by the magnetic field and the current. Meaning that a particle, when it's introduced into a magnetic field, it gets force applied. It gets accelerated. So you can use the acceleration to connect to mechanics and actually do some mechanics. So for example, a classic example is that if you have a magnetic field that points toward the inside of the paper, and you introduce a particle, let's say an electron, into this field, then this field, first of all, to which direction would this particle get applied force? Let's use FBI. F is the direction of the force. B is the direction of the magnetic field, which will be towards the inside of the paper. And I is the direction of the current, which is the opposite direction of the movement of the electron, which will be leftward. Thus, you would have force applied towards yourself here. Now, that being said, you can realize that I draw the magnetic field wrongly because you will have to draw it longer towards the bottom. But anyways, now what's going to happen is that you have F pointing towards downward. Thus, this electron that you have over here is going to curve until it goes out of the magnetic field again. I hope this makes sense, right? Now, what's interesting is that at a given point, for example, at this point, think about it, you would have two forces clashing. First force would be the magnetic force, the force induced by the magnetic field and the current. Now, the other source of force would be the centrifugal force, R under mv squared. Now, what's interesting is that in order for this electron to make this curve the path and get out of this magnetic field, the two forces should be the same. Or else, it's going to either just move towards the center of the circle if F is greater than mv squared over r, or it's just going to exit the orbit. It's just going to fly away if mv squared over r is greater. Thus, this F, the magnetic force, which is BVQ, should be equal to the centrifugal force you have. Now, with this, what you can figure out is you can figure out the radius, because you can just use simple algebra, and that would give you mv over pq. Now, something like this, well, this is one specific example, although this example, this scenario is going to appear a lot. So it's going to be really helpful if you understand this relationship between the centrifugal force and the magnetic force. But anyways, this is one example. You might encounter a different example in your AP exam, right? So it's more important to, instead of just understand this one scenario, try to understand how the force applies in which direction, and how the force can act, the magnetic force induced by the magnetic field can react with other types of forces like centrifugal force or any other type of forces in order to make a specific type of move. For example, in this case, that move was a circular path. In other cases, I don't know, the particle might stay in equilibrium because the net force is zero, because they all cancel out, or something like that. There might be different variations, but just try to understand how you can connect force caused by the magnetic field to other things. So that was it. That was it. Sorry if I didn't make a lot of sense in this video. I mean, I'm so tired and like I'm drained out. But I hope I made a lot of sense in this video as well. Thank you for watching this video. Don't forget to have a great day. Don't forget to relax. Don't forget to chill. Don't forget to actually be more energetic when you're taking the test, because you don't want to be like me right now when you're taking the test and you will just make a lot of mistakes. Anyways, thank you for watching my video. Don't forget to have a great day. Bye.